Buenos dias. Come on. Give me some love here. Hola. Thank you very much. Thank you very much. So the rest of the talk is going to be in English, because obviously that's about all the Spanish I speak. My name is Richard Warburton. I'm the co-founder of a company called Opsian, who run production profiling software for companies. And I'm here to talk more generally about production profiling, how it could help you and your organization, and what the benefits are you may get from it. So the first thing I'm going to talk about is why performance might matter to you and your organization. Obviously, performance problems are really fun problems to solve, but I'm going to take a bit more of a business perspective, say why you might want to address that kind of thing. Then we're going to talk a little bit about why the development and production environments are quite different, why looking at performance problems on your laptop or your desktop might lead you to draw some erroneous conclusions and optimize the wrong things. And then we're going to talk a bit more about the distinction between, say, profiling and existing monitoring solutions, and then how you can actually do profiling in production. Because for a lot of people, it's just a lot of tooling is just too high an overhead to actually generally use in production. But we can, in 2018, do that. So the first thing I would say is customer experience. Now, when people think about customer experience, they often think about how nice is the UI or the UX on your website and things like that. But there are other more qualitative aspects of customer experience, like, for example, is your site really slow and unresponsive? Is it really annoying for people to use? Is it a site that goes down under heavy load? So these days, who uses, say, Facebook in order to talk to their friends and family and things? That's quite a good number of people. What about WhatsApp? Who uses WhatsApp? That's loads of people. Who uses Friendster? That's nobody. Of course it's nobody, because it's a company that doesn't exist anymore. And the reason they don't exist anymore is because they constantly had problems when their site was ramping up. And when lots of users were using their site, they just couldn't keep up with the load, kept on falling over. And as a consequence, are no longer a player in a huge social media industry where other companies have public valuations of multiple $100 billion. Then there's this kind of weird thing that we don't really talk about that much, which is responsive applications can often make more money for your organization. You want your software to be like the Flash. This conference is clearly all about superheroes, so I think the Flash is the superhero who's most responsive, most agile, most fastest. So a number of companies have run these kind of big A/B test studies looking at what the revenue impact is of slower and faster software. eBay published studies years and years ago, but it's kind of getting even more interesting these days. Amazon published a study showing that if you added 100 milliseconds of latency, that's really quick. That's quicker than me clicking my fingers quick. 1/10 of a second. So that cost them 1% of sales. That we're doing like an A/B test on Amazon.com. It's just a very, very short piece of latency that they added in there, and it cost them 1% of sales. That's a huge amount of money if you're Amazon. Google also published a really interesting A/B test, which they did on their search page. They added half a second, 500 milliseconds, of latency on search page generation time, so just a half-second lag to those search results popping up for you. And they found that traffic dropped by 20%. That's huge, right? I mean, we are so impatient that if a website takes an extra half-second to load, we'll literally browse off, we'll do something else in the browser. That's huge. So, if you want to keep your users' attention, if you want to keep them happy, you want to have nice, fast, responsive pieces of software. And the other reason why I think it's always worth us thinking about evaluating and understanding performance problems in our own stack is reducing infrastructure costs. Now, obviously, developer time is pretty expensive, so you don't want to be trading off lots of developer time to solve these problems for infrastructure costs, but it's always worth remembering that, especially in modern cloud-based environments where you get charged per unit of compute time, per disk IO-op, per byte being sent over the network, that these costs scale up and down with the amount that you use those computational network and disk resources. So you can see a direct saving in terms of your cost base from writing more efficient software. And obviously, it's a little bit more environmentally friendly as well, which is fantastic for everyone. Okay, So hopefully you're, if you weren't already, enthusiastic about trying to improve the performance of your software and thinking about performance problems and solving performance problems is a regular thing. Now, when most people investigate performance problems they see in their software application, they'll do it in development. They'll do it on a laptop that they're using to write code on, or a desktop in their office, just in the same way that they would do if they were, say, investigating a functional test about their software, if they were trying to see if it was correct or right or wrong. Now, whilst running things like unit tests, integration tests, automated testing on your development environment is absolutely fantastic. It gives you really quick, agile feedback as to what's going wrong with the correctness of your software. It's not a very good approach to understanding the performance characteristics of your software. That's because your development environment and your production environment are often two completely different things, and writing performance tests is really hard. So, firstly, there's the question of unrepresentative hardware. Okay, so raise your hands in the room if you have the exact same hardware that you use in development as your production system is. The exact same CPU, memory, disk I/O, one person in the room. Exactly as expected. You often have very, very different hardware in terms of your development environment and your production environment. That's not a crazy thing for you to do either. Who wants to be lugging around like a massive 12-core Xeon server on their back when they want to go and code in a coffee shop? I don't want to do that. So we have very, very unrepresentative hardware. Now, it can be unrepresentative in a number of different ways. You can often get CPUs which have more or less cores than your production system. You can also get CPUs that scale things very, very differently. So a lot of production-level Xeon servers, for example, have CPU power management facilities that keep them ticking along at their optimal clock speed very consistently, whereas things like laptops will vary their clock speed depending upon the heat output. They'll have this nice speed boost stuff going on. Speed boost sounds great. It means you can burst for a little bit and get some nice performance, but then your laptop will kind of slow down. You can get very, very erratic benchmarking results as a result of this. Now, historically, you might have said to yourself, don't worry, Richard, it's okay. If it works okay on my laptop, it'll work okay on our production hardware because, you know, the laptop, it's cheaper, it's slower than production hardware. Now, there's an element of truth to that, but there's also a fact that certain problems manifest themselves differently. They behave differently in a production system than, say, a small laptop. If you've got a laptop with 2 physical cores or 4 hyper-threaded cores, like, say, this one, you'll get very different lock contention problems from happening on a big server. You might be able to get away with writing a piece of software that's got 1 or 2 big fat locks in the middle of it that all your code's contending on, and you won't get away with that on, say, a 30-core server. Another aspect of it is if you ever use modern cloud-based environments, you'll find that those much, much smaller servers, and especially things like the AWS micro-instances, can often be much slower than the hardware you have available on your laptop. Or maybe you have beefy hardware there, but you're sharing it with a noisy neighbor, somebody else who's running really, really fast or computationally expensive work, or even worse, disk I/O intensive work. Then there's a question of unrepresentative software. So, down to the operating system, who's running the same version of software in their development environment as they are in production? A few people. Awesome. That's great, but not really necessary. Again, a lot of people love using things like Mac OS, they love using Windows 10, they don't necessarily want to have to use Linux on their desktop, though I also love Linux on the desktop. But in a production server, you may well be running Linux. Even if you're running Linux, this graphic demonstrates the massive family tree of different Linux distros, how they all spread out and how they change over time, and how many different versions we have on the far end of that graphic. Very, very different environments. Now, you might be saying to yourself, Richard, don't worry, you know, it's not exactly the same thing, not exactly the same patches, but we're using something basically similar. Well, about a month and a half ago, in response to some of the Spectrum Meltdown patches, Windows 10 released an update. And that update, when I was doing some benchmarking on it, reduced UDP performance, networking performance of sending UDP packets in terms of throughput by 40%. That's huge, right? A 40% drop in networking throughput off one single security update. That's the kind of different thing you can get as a divergence between different versions of software. And that's just two different versions of the same OS a week apart. I've also seen some interesting examples of things like people upgrading from Java 7 to Java 8 previously and having massive slowdowns, or in some cases speeds up. Most people improve performance, but there was one organization I was aware of where a key piece of their software had a 10-fold slowdown moving from Java 7 to Java 8. And the reason why they had that slowdown was just the difference between moving from server mode compilation by default in the JIT compiler to tiered mode compilation by default. One little configuration option, which could be flipped back after the fact, had a 10-fold slowdown in terms of their software. Big difference just on small things like that. Then there's the other aspect of understanding performance problems in development, which is how representative is the actual workload that you throw at your system. So it's all very well, even if you've got the same hardware, the same software, correct and equivalent configuration between the two things. But if your load test, if your performance test that you're throwing at your software in development is not the same as what's happening in production, you can get very, very different results. So for example, do you understand what the distribution of different page loads on your site is? Do you understand how lightly different pages are to hit? Do you understand what the difference in the distribution between different users is? I've seen people do things like write performance tests where all the requests in their web application are run through one user. That one user sits there nicely in some cache in their software, and they never take a hit for looking at that user. In production, they get lots and lots of different requests from lots of different users, has a very different impact upon the way that kind of cache behaves. And also can have a very different impact on the way your website performs as a whole, as to whether things fit inside a cache or don't fit inside a cache. You can get also quite different behaviors if you are running multiple different connections from different hosts coming to the same system versus one. Lots of different aspects of your workload. Very, very hard to get performance tests that are realistic and representative and look like a production system. It's a very specialist skill, and it's really hard to get right, and really time-consuming as well to get right. Then there's the fact that JVM might have very different behavior in production to in a development environment. It does adaptive optimization in the JIT compiler. It will profile at a very light level, so it will record, for example, the number of times different methods are called, and only JIT compile methods once they've triggered a certain compile threshold. Now, if you warm up your application differently in a development environment to a production system, you can get different methods JITted, and that can have impact on optimizations. Sometimes you even get weird behaviors in production. For example, one system I was aware of had a clustering system which had a strong leadership concept. And when you had your leader on one system, it would receive a bunch of messages, process them. All the business logic on that system would be nice and hot. It would get JIT compiled, perform really well. If you had a split brain system in a cluster, it had a nice, correct leadership algorithm, would fall over to a different machine. Worked very nicely. But if that failover happened at the time that you were experiencing a peak throughput or a heightened level of throughput, the system that it failed over to wasn't running all the business logic that the leader was. So it had to jump into interpreted mode for that business logic, at least at the beginning. So you had a situation where you'd have a failover to another node, things would work okay, but they'd be much slower for a while until the JIT compiler caught up. And sometimes you have adaptive optimizations which assume certain code is never called that the JIT compiler then needs to back out of when you get things like leader-follower failovers. So there's a lot of things there which are very, very hard to simulate in a development environment. Now, this dog looks cool, but you don't really want to be this dog. You've got no idea what your production system is necessarily doing when you write load test performance tests. That's not about being really stupid or really smart. That's about the fact that there's unknown unknowns, things that you won't know ahead of time about the way your system's going to behave in production, that you can only know from seeing it. And no matter how smart your performance tests are and how representative an environment you get, there are often differences, and most people don't have representative hardware or software. So in practice, development and production often behave very, very differently. Okay, so hopefully by now, I've convinced you that you want to really understand performance problems in production rather than on your desktop or your laptop. So what methods do we have for understanding that? Well, there's a lot of existing performance monitoring tools out there that do really, really good and useful jobs. So let's have a look at some of the different information that these tools can gather. The first thing that you see almost ubiquitously everywhere all over the place is metrics. I like to call these things, ambient metrics, passive metrics, system metrics. So regular numbers about the behavior of your system that you've pre-configured. Things like how much of your CPU time is being used, or what the breakdown of that CPU time is between, say, user and system time. Things like page load times, all sorts of metrics about lots of different aspects of your system. People often put in metrics around throughput on queues or databases or things like that. Metrics are really good to be collecting. They're really cheap to collect. You can collect them with very, very little overhead, very, very efficiently. And they can often be very, very effective as well. But the problem with metrics is they sometimes don't lead you to the exact heart of the problem. You often have to look at something else, especially if it's telling you the problems within your software, within your code. You need something else to narrow down where the code is. That's why a lot of monitoring systems do some kind of instrumentation. So instrumentation means when some part of your system runs, the monitoring tools add in or instrument, they add a little bit of extra code. So for example, suppose you're using, say, a Spring web application, they'll put in a little bit of measurement time in your controller layer and say, hey, requests took this long to go through the controller layer of your application. That's pretty good, that's pretty useful. It can tell you a lot of more narrowed down information, can let you track back from those big picture metrics that tell you what's going on or not going well in the large back to a specific piece of code. But the problem is that instrumentation takes time itself to run. So the more fine-grained some instrumentation you need for your piece of software, the more instrumentation, the more code needs to be added into your software stack. And that slows down the application that's running under it. Sometimes this instrumentation can be well designed and not slow things down very much. Sometimes it can slow things down a lot. And the other aspect of instrumentation is you have to think about it ahead of time. So instrumentation is very good for telling you, say, for example, hey, you've got a Spring app, I'll know what different components within your system are doing what, and I'll instrument those. Instrumentation is much less good at trying to identify specific bits within your own code or slow components within your own stack that it won't know about, that there's not a general pattern about. Okay? Then there's production profiling. So profiling doesn't make those kind of specific assumptions about instrumentation. It could be implemented in a variety of different ways, but it's just trying to tell you how much of certain resource is being used. So, what methods are using up your CPU time? What lines of code are allocating the objects that are eating up your memory? You can get some profiling for very, very low-level or fine-grained things like looking at CPU cache misses, all sorts of fun stuff in there. Probably goes a bit too far for most developers in many cases. Now, production profiling can be automatic. Once you've got a profiler that works, it doesn't matter what your app is. It doesn't matter if it's a Spring app. It doesn't matter if it's a micro-profile app. It doesn't matter if it's something you've built yourself from scratch, something more bespoke or custom if you've got customers with more differentiated or unique needs. The problem with profiling that a lot of people have is that the sheer overhead of running profiling in production can be really, really invasive, right? It can slow you down a lot. But, as we'll see a little bit later in this talk, it doesn't have to be that way. We can be smart about the way we write profilers and get really, really low overhead. But that's the general point, I would say, about production monitoring and production measurement systems. It doesn't matter how fast your software is. If your software is flying along, but you're carrying the big weight of some monitoring or measurement tools, it will slow it down. Just in the same way as a lot of developers experience performance problems from logging too much debug information out in production, you can do the same thing with performance monitoring tools. And you want to always be the solution or a way to help people find the solution to their problems rather than being the cause of those problems. Yeah. So I mentioned the cause of the problem, the overhead problem, but there are other more kind of psychological things around the information that you get provided. Now, if you have too little information that you're getting back from your production system, you can't understand the production problems. But if you have too much information, if you get all the metrics from all the graphs in the world, it can often lead to a needle in a haystack problem where you're looking around to see what the problem is. My favorite metaphor that I've heard for this kind of diagnostic approach is like a murder mystery debugging style, where you go through the different things that your system's doing, and like, you know, at the end of, say, a Hercule Poirot mystery or something, you go through and accuse all the different components in your system. Is it you? No, you're okay. Is it you? No, you're okay. It's you, isn't it? It's always the last thing that you look at, which is the problem, just like the murder mysteries. So I think there's a kind of trade-off here, like the three bears with the porridge, where you want to have not too hot a porridge, not too much information that leads you to look at the wrong things, and not too cold a porridge, not too little information that means you can't understand your production performance problems. Then, going back to these metrics, as I said, metrics are really good for letting you narrow things down. And they can often be graphed with all sorts of pretty lovely graphs. You kind of see these systems that people have, these dashboards that have where they are colorful, color-coded, all sorts of things. But in order to actually be useful to you, when you have a problem in production, you need to be able to progress treatment. You need to be able to find out what the problem or problems are that need to be addressed. You need to figure out what's going wrong there. And unless you can directly track back those metrics to something you can fix, they're not independently useful. You've got to combine them with some information to help you do that. Another thing that you kind of see a lot when it comes to systems, especially systems with too many metrics or too many alerts configured, is what I call normalisation of deviance. So that's actually a term that comes from some sociology research. So you often see normalisation of deviance more in a development environment. So who's worked on a team, don't worry, don't be shy, we've probably all done this, where this sentence has been said, look, some of our tests are failing, so let's just ignore them or switch them off. That's like nearly everybody in the room. If you're not putting your hands up, well done, it's amazing. I'm sure nearly everyone has experienced this kind of situation. But you get a similar thing with alerting problems from monitoring systems. Sometimes these alerts get triggered, so we just ignore them or we switch them off. I've been on consulting engagements where I've walked into organizations. They've had these amazing big dashboards, like on huge 50-inch plasma screens, very expensive, all the gear. And you look at those dashboards and they're like, green, green, green. Why is this one red? Oh, it's always red, Richard. Okay, so why is it displayed at all then? That's the other question you have to ask yourself. These false positives have a cost. If you don't use those things, you want to switch them off because people, they'll ignore them. And if you think one of them's red, maybe the one below it will start going red, and that will be important. You just won't notice because you're used to seeing a bit of red at the bottom of your dashboard. Alert false positives have a big cost. Now, if we ended the talk here, it would be a bit of a downer. I've only really talked about problems and issues that you have, but surely there's a better way. I think a lot of people combine metrics with some instrumentation in their system to find out what's really going on in production. But what I'd actually like to talk about is combining the idea of metrics with production profiling and seeing where the production profiling can help. I've already mentioned it's framework agnostic, but can we actually do profiling in production? Well, yeah, we can. It's in the title of the talk, isn't it? That's a bit of a cheat. But what I mean is most people don't think we can do production profiling, and I'm hopefully here to convince you there's better ways or worse ways of measuring and doing profiling, and if we use some of the smarter ways, we can do it more efficiently. So, firstly, why would we want to use production profiles? Well, if we've got a specific performance problem that we encounter in production, we want to find out or understand the time period or what machines it affects in your system. We can have a look at the different types of profile depending upon what resource we think we're bottlenecked on. Looking at CPU versus wall clock time, I'll explain what the difference is there in a minute. Or maybe you're looking at memory profiling. Maybe you're looking at what objects are being allocated in your production system. You kind of want to see what the real consumer of a given resource is. What's the bit of your code that's eating all the CPU? What's really slowing you down? Fix it, and then deploy and iterate until everyone's happy. Okay, so production profilers, very, very simple to use in many ways. They just tell you where your resource is being consumed. That's the bit of the problem they're solving. Now, something which I think is always kind of glossed over when we look at profilers in Java times, a lot of profilers tell you, hey, here's some time that's been allocated to memory, to a method. But they don't necessarily tell you what kind of time it is. So I like to think about a distinction between CPU time and wall clock time. So CPU time is the time the code is actually spent on CPU, using up CPU cycles. Simple, in the name. Wall clock time is a little bit harder to understand. Wall clock time is the time from when you started an operation right through to when it's complete. So it could be time when you're spent on CPU. It could be time when you're spent blocked because you've got loads of other threads running on CPU. It could be time you're spent sitting waiting on a big lock or a big synchronized block in Java terminology where another thread's got that synchronized block and you can't get in to run. A metaphor I like to think of in order to understand that distinction is a bit like, perhaps think of your favorite lovely local coffee shop, or if not, Starbucks. When you want a coffee, there's two parts to this time, right? Firstly, there's the time you spend sitting in the queue in the shop, waiting to be served. And then there's the actual time that people spend making your specific coffee. So CPU time is a little bit like the time spent actual making coffee versus wall clock time being the whole time, the queuing time and the actual execution of the coffee task. Profilers tend to provide a variety of different views that let you visualize this information. So the simplest view that you can get in terms of a profiling system is just a hotspots or flat profile. So hotspots is a way of just taking a list of the methods, sorting them by the amount of time that they're using, and putting that at the top. So you can see where the bottlenecks are. They're the methods which are using up most of your time. Some hotspot profilers may tell you about line-level granularity, where the exact lines in your code are using up. Some profilers may not. Tree views are another really common profiling visualization. So a tree view is where you have a big tree of methods, and the methods further up the tree are calling their children. So they're executing their children, and then you can get a breakdown within each point of the tree how much time that sub-branch of the tree is using. Now, a more modern, exciting visualization is flame graphs. Have a hands up who's heard of flame graphs before? Awesome, awesome. That's a good number of people there. They're gaining a bit more popularity. That's great to see. So, flame graphs are a visualization that I think originally should be attributed to Brendan Gregg at Netflix, who I think has done a lot of work popularizing them. So a flame graph combines the idea of a tree view's method level hierarchy with a visualization of how much time different things are using up. So in a flame graph, the methods at the top are calling methods below them in a flame graph. Some people invert it, so this is going top down in that visualization on the board. Some people would go bottom up, where the methods higher up the flame graph are being called by ones lower down. And how wide the box is within your flame graph indicates how much time that method or its children are using up. So you can see, for example, methods that have big self-time, big amounts of time where they're running code within that method, have wider areas below them. And you can see what's calling what and what the context is of the method that's using time. Pretty cool and pretty useful. Now, the way the first kind of set of profiles that you might see are implemented is through instrumentation, basic instrumenting profilers. So if you take the open source JVisualVM profiler, click the Profile tab, this is what it'll do. It adds some instrumentation to collect timings, so at the beginning of every method, it'll take the time at the start, the time at the end, subtract away the difference, and record the amount of time within that method. Now, instrumenting profilers, you might think are pretty accurate because they measure all the different points in the program, but actually they tend to be quite inaccurate. And the reason why instrumenting profilers tend to be quite inaccurate is because they modify the behavior of the program. Not just by adding a little bit of instrumentation, like smart APM tools do, but by instrumenting everything. So if you think about a basic Java getter or setter method that's just, say, reading a value out of a field and returning it, that's a really cheap operation compared to calculating the amount of time that operation takes. If you've got a really long method that's doing a lot of computational work within it, the overhead of running that instrumenting code is very small. So because the amount of overhead of the instrumentation itself differs based upon faster or slower methods, you actually tell users that your that your quicker methods are working slower than they really are as a proportion of the time. The other problem from an instrumentation profiler point of view, if you're looking at using it in production, is they tend to have higher overhead, like 2-3x is not unusual. Okay, so what about sampling or statistical profilers? Sampling and statistical profilers have some part of your application that's executing. So here we've got a stack where your web server's got a thread that's running. It's got a controller that's going to read a person up, instantiate an object, and do some view code, various bits and bobs. And sampling profilers periodically interrupt the stack that's running, and they take a view, a snapshot of what's running on the stack at that point in time. So they will have this periodic interruption, they'll tell you what's on the stack, then they'll aggregate those views, aggregate those snapshots of the stack to produce one of the views earlier. So they're probabilistic, but these offer much lower overhead because you can decrease the sample rate to reduce the overhead, and because it doesn't have to instrument all the code in your application, it doesn't have to add that much extra code to be executed. But there's a big problem with sampling profilers. So you see, the thing with profilers is that they're often a little bit like politicians, right? They can tell you one thing, and the reality a little bit different. They can be a little bit dishonest. So how does that manifest itself with profilers, sampling profilers? Well, in Java, the most basic API for you creating a sampling profiler is using the standard JVMTI getAllStackTraces method that stops all the threads in your application, looks at all the stack traces, gathers that information, and then returns it back to you. The problem with that approach is it has to stop all the threads. All the threads in your application have to come to a halt in order to read those threads at that point in time. So how does it do that? Well, the same way the JVM uses to interrupt your application to do anything else. It uses, for example, initiating garbage collection pause is the same method. And that is using safe points. Safe points have a little bit of polling code that gets instrumented all over your application, where it just reads the safe point poll, and that safe point poll is basically just reading a value out of a page somewhere. When your JVM wants to interrupt the application, it takes that page of memory that you're reading data out of and protects it. It puts an interrupt handler on it, and the OS and the hardware combine together to say, look, if someone tries to read something from that protected page, we'll call this code over here. The execution of your program then slews off, runs whatever your VM operation is that you want to run, for example, reading all the stack traces, and then goes back to normal. Now, the problem is that getAllStackTraces in the JVM basically entails n+1 safe points. It causes a safe point for every thread that you want to read in some JVM versions. That's a lot of overhead. The safe points themselves alter the way your application's working and slow you down, adding more overhead. And there's also this bias of safe points. Safe points don't happen everywhere inside your application, and the JIT compiler will optimize away safe points from certain points, like the heads of counted loops, like for I equals 0, I less than n, I plus plus, will be a counted loop. And it will optimize away the safe points from the heads of those loops. And that means you can get periods of time where there's no safe point to elapse. And as this diagram shows, you can get multiple samples which would be doing other things attributed to a different point in time where a safe point happens. So there's a bias there. It's not telling you exactly what's going on. All right. Don't worry, there's a better way of doing this. So to get a sampling profiler that works well in Java, you have to do a couple of different things. You have to interrupt the thread itself to run your profiling code, and you have to walk the stack. Now, the lowest overhead way of reliably interrupting the JVM, at least on Unix-based operating systems, is to use an OS signal. So you're probably pretty familiar with sending a kill or a kill-9 to a process to say, look, quit, or like really, really quit right now. You can send other profiles, you can send other signals through the same operating system mechanism. For example, there's a sigprof signal that comes with Unix operating systems that periodically send a sigprof that lets you register a callback handler that will do some profiling operation at that point in time. The JVM has a signal handler safe method built into it that's not used by most JVM profilers, called async get call trace, that lets you walk the stack and collect the information around there. It's a bit fiddly to implement some of these things because you have to write signal handler code, which is a bit icky. You can't do a lot of things, like you can't even malloc any memory inside a signal handler, for example. But it does work really well. It's much, much lower overhead. It doesn't have safe point sampling bias. It's a massive win. Now, there are some open source Java profilers that you can use. So there's a bunch of things you're probably familiar with, like JVisual VM, Twitter CPU get profile, hprof, things like that, which are all really, really high overhead, and use the traditional get all stack traces type approach or something similar to that. Some open source much, much lower overhead profilers. There's the async profiler on GitHub project. There's Honest Profiler, which is a project that I maintain. And Java Mission Control has been open sourced from 11 onwards as well, that doesn't necessarily use async get call trace, but uses a very similar method that also has operating system signal handles. So those are much, much lower overhead and much more accurate for on-CPU profiling. You can also use profiling support in the Linux kernel. There's tools like perf, eBPF. I don't really want to go into much detail, but you can look at the perf map agent project again on GitHub. So these use the OS's perf mechanism for doing profiling, and that lets you map it back to Java code. But the problem with profiling in production isn't just the overhead of running the profiler itself. There's a bunch of practical issues that those open source projects still have, even though they have low enough overhead to run in production. The problem is that you often have, when you're running a production system, a mass of different machines, different servers and different services that you're using. And you don't want to just have to connect to one individually, switch on a profiler, get the data back, deal with that aggregation of data problem, deal with the overhead and the hassle of connecting to it, especially in a situation where your production system's under load and may even be difficult or impossible to connect to. So that's a very big barrier for ad hoc profiling. It's the sheer effort of doing it. What you want to do is you want to automate these things. And I think it's a good thing to think about profiling all the time in production. It massively reduces the barriers to overhead and the problems that you get from connecting into a production system when you have a high period of load. The other benefits you kind of get from always-on production profiling is you get this historical data. A lot of people love the historical data that they get from metric-based systems. Why not do the same thing with profiling? It allows you to do post-hoc incident analysis. So that means you've had a problem, you did some temporary fix just to get things working again and keep customers happy, but you've still got that data after the fact that you can look at to understand a more strategic solution, a better long-term solution. You can correlate that data with other metrics, other systems, with what your database was doing, all sorts of things like that. And it also enables you to understand performance regressions. You release a new version of your software, you can see how it performs compared with the previous release. Aggregation, indexing. Obviously, very, very few people run a single process, a single instance of their production system. Even if you've got a big monolith, you often may have that cluster to have multiple instances running. Desktop profilers just don't really cope with the scenario at all. Their whole UI model is we'll profile a single process, no concept of aggregation. So aggregation, really important. And the other thing is having context for what you're doing, keeping things like the version of your application, keeping some environment parameters, where the machine is, the location, the CPU, a machine type, things like that. Desktop profilers, again, have no concept of this information, and again, are problematic for doing production profiling for this very reason. But it's information that's really, really useful for you, and existing APM tools are really good at providing that kind of information. So, summary of this section, production profiles possible? Yes. We can do it all the time, we can do it with really low overhead, and it can give you deep insights into what your code is doing. A lot of the problems people think of in terms of overhead, they can be solved with smarter profiling methods. Cool. Let's wrap things up. So in this talk, I talked a little bit about why performance matters, why you might want to do it from a business point of view. We said performance testing and development seems cool, but often there's so many problems and it's so time-consuming, it's difficult to get reliable, correct results compared with actually looking at what your production system is really doing on a real workload. Metrics, pretty cool, but hard to action sometimes. Hard to look at just on their own in the abstract and see what the exact problem is. Instrumentation, also pretty useful for narrowing down problems, but very, very hard to get instrumentation that gives you method-level granularity, that takes an arbitrary bit of Java code and says, this is what causes the problem. Too high an overhead to instrument everything. Production profiling, very, very few people do it these days, but it can provide loads and loads of insight. You can profile arbitrary Java code. It doesn't have to just be the big picture items. It provides a lot of insight and can be really, really low overhead. Cool. So I'd love us to take a bit of an attitude shift on profiling and monitoring, looking at doing more profiling in production, okay? I'd love to think about these problems as being systematic, not ad hoc. Things where you have a regular process, a normalized way of understanding performance problems, rather than just, oh no, something's gone wrong in production, let's try and do anything we can to fix it immediately. Something that's a bit more systematic, a little bit more thought through. Being proactive, not reactive about performance problems. That doesn't mean wasting all your development time fixing, hyper-optimizing code that doesn't need optimizing. It means understanding what the business goals and trade-offs are and putting in place systems to understand what your production system is doing rather than just reacting to when there's a problem. And production profiling can be part of that and really useful, especially if it's always switched on and historical data is kept and stored. So, if you take away one thing from the talk, hopefully this is it. Please do production profiling. Please do it all the time. It's really useful. You will love it. I'm sure you will love it. Fantastic. Thank you very much for listening to this talk. I hope you enjoyed the talk, and if you have any questions, I'm happy to take them now. Hey.
As we know, we have new releases of Java versions, and Oracle recommends. Am I audible?
Yes.
Okay. And Oracle recommends that we test our code with the new versions, even if we are not deploying that to the production. So how can we do that? How to go about it? Because if I'm only checking out my code on development environment just to iron out any issues that I might have, but that would not be actually ironing out the issues that I might have with the production system. So should I do that? Should I not? And if yes, how?
Wow, there's multiple questions there, really, aren't there? So I think the big gist of it is there's new Java versions being released all the time, 10, 11. Should we keep on testing them? And I think that depends a lot upon what your company's plan is for moving forward. Like, a lot of people are not, for example, releasing 9 and 10, just jumping to major long-term support versions like 11. If that's the case, I would just test those major LTS releases or do some functional testing to see what's going on during the intermediate time. As to how you do that development testing, how do you do that testing of different JVMs in production, if you've got a system that's clustered and has a load balancer and that you can then have the option to send a certain small percentage of your traffic or even a duplicate copy of your traffic to some machines, that's a very effective way of testing. I've seen people do that where they do basically canary deploys. So they roll out a new version of some software and they don't roll it out to all the machines in one go. They just canary 1 or 2 and roll back if there's a problem. It's quite hard. There's a lot of infrastructure you need to get right to do that effectively, but canary deploys are a good solution to that kind of problem. If you're looking at more development correctness side of things, most CI servers like Jenkins has a matrix view where you can do things like run the same build but parameterized. And one of the parameters I've done for testing code that I've shipped to clients where I want it to run on different JVM versions in the past is have CI set up running the same JVM, generally the same Java code against multiple JVM versions. That's another thing you can think about doing as well. Cool. Any other questions?
Yeah.
Hey.
So right now we are using a lot of distributed system, microservices and everything. I'd like to know how you apply production profiling in this, because mainly we don't have so much CPU problems, more like network problems. And you spoke about aggregation and automatization, but you can...
Yeah, so I think there's 2 things to think about there. There's one of them is how do you solve the problem of profiling over different services, and there's things like open tracing, distributed tracing that solve that kind of problem. In terms of how production profiling on box can help you resolve that kind of problem, a lot of the times you'll see people who have microservices related problems. They basically don't really have a microservices related problem. They more have like a bunch of remote network I/O calls that are blocking in sequence one after each other. And if you're using a traditional Java threading model and a wall clock time profiler, you'd be able to see those kind of problems where you're basically blocking waiting on remote services just with existing profiling tools. But yeah, if that's not something you're keen on, or for example, that can be harder to spot with some of the reactive tooling, for example, then looking at things like distributed tracing, open tracing is an example of that. Okay. Were there any other questions? Hey.
So going from no production profiling into profile everything all the time, there's a first initial gap more on your organization or having a discussion with the ops team, with, I don't know, someone in management approving this budget. Do you have some initial recommendation on how to tackle this first
social
aversion
problems.
to adding something new into production that may have a negative impact? How to tackle this this negative reaction from the rest of the organization?
I think the first thing is to try and make sure that you're doing things that have as low an impact on production as is possible. So things that are doing very, very low overhead, sampling-based profiling can be less than 1% CPU overhead. Don't necessarily need to add instrumentation all through your code stack, which can have risks associated with it. So an example of the kind of risk that you might see that was a problem that bit a lot of people doing instrumentation-based stuff was, for example, when the JVM bytecode verifier got tighter about what was the first call in methods always be on. The first control in constructor methods always being a call to the super call, which was previously enforced at Java C time, but not at bytecode verification time. And then I think mid in the 8, like an 8 update release or something like, switched that on there, and people have been instrumenting beforehand, before the super call, and things broke. So again, trying to be careful about what you do so it has lower risk and lower overhead is really good. I think another thing that is really good to think about is balancing those risks off with the pros of what you're getting, the production observability, visibility, insight, that are beneficial to reduce business risk in the long term, reduce infrastructure costs, and get a better, happier customer user experience as well. So I think trying to explain those pros in business terms is often something that's helpful. And finally, again, things like canary deploys or rolling them out to a limited set of machines that you've load balanced so you don't have everything falling over can reduce the risk of rolling out any new thing into production as well. So those are the three things that I would say. Cool. We've just finished time, but I'm going to be here for the rest of today and some of tomorrow as well. So if you've got any more questions, just come and talk to me afterwards. Thank you very much.